In this unit, we're going to look at thermal physics. We're going to start off by taking a look at temperature. So our senses help us gauge how hot or cold something is, but they're not very precise, and you can't use your hand to determine if the oven is the right temperature for baking cookies, for example. So we need a precise way to quantify temperature. So historically, there were several methods that were developed. One of the early ones that caught on was the Fahrenheit scale, and it used two temperatures, the temperature of really cold brine, which is super salty water, at 0 degrees, and then the human body temperature was pegged at about 100, and that's not quite right, but it's close, 98.6. Later on, we used fixed transitions of pure water, the melting point and the boiling point, for the Celsius scale. And then even later on, we developed absolute scales, which we'll take a look at here today. So converting between temperatures is pretty easy. We know that water freezes at 0 degrees Celsius, which is 32 degrees Fahrenheit. So I can make that a point on a graph. Water boils at 100 degrees Celsius, which is 212 degrees Fahrenheit. So using those 2 points, I can develop an equation for a straight line, and I can relate the y to the x. So equations for straight lines are always y equals mx plus b. On the y-axis, we have the temperature in Fahrenheit, so that's over here. On the x-axis, we have the temperature in Celsius. The slope we can calculate as 1.8. That was the warm-up today. And the intercept is where the line crosses the y-axis, which is at 32. So this is an equation which represents the relationship between the temperature in Celsius and the temperature in Fahrenheit. And that's in your toolbox. That's this equation right here. And if we solve that equation for Tc, we'll get this one here. The temperature in Celsius is the temperature in Fahrenheit minus 32, and then all divided by 1.8. So it's pretty easy to convert those. If you have a temperature in Celsius, you're simply going to take 1.8 or 9/5 times the temperature in Celsius plus 32, which gives you 104.5 degrees Fahrenheit. And so you would not go to school on a day like that. You clearly have a fever. So although we could quantify temperature, we really had no idea what the heck it was. So the first person to sort of get an inkling of what was going on was a guy by the name of Robert Browning. He observed tiny particles of pollen on water and noticed that under a microscope he could observe these guys jiggling or moving. And trying to explain this led scientists to an understanding of what was going on. The water molecules are actually in motion, and as they bash into the very lightweight grains of pollen, they knock them side to side. So these are getting jiggled because the water molecules are in motion. So if you make the water hotter, they jiggle faster. If you make the water colder, they move a little less. And we can quickly tell that the water temperature has something to do with the speed of the molecules and how much they bop these pollen grains around. So what we now know is that all atoms are in motion. They have kinetic energy. They move through space, they rotate, and they can kind of bounce. You can imagine the molecules, the hydrogens and the carbons connected to each other by little tiny springs. They're not really springs, but they act that way. And they can kind of bounce between those and oscillate on the bonds. All of this motion is kinetic energy, but it's kinetic energy that's associated with the molecular motion, and we call that thermal energy. So if you ask, what is thermal energy? It's the kinetic energy associated with the motion. And temperature is sort of a measure of the average kinetic energy that each molecule has. So you might remember our bubble map from Unit 3, the types of energy. We talked about gravitational potential energy and how chemical energy is converted from gas to kinetic energy, for example, in a car. Today, or this unit, we're going to talk about heat, which is a form of kinetic energy. All right, so thermal energy is the energy that is associated with the motion of molecules. That's going to be our definition of thermal energy. Heat is going to be the transfer of this energy from one form to another. So when energy transfers from one form to another, we're going to call that heat. And we are going to call temperature a measure of the thermal energy. Okay? So those are our definitions. You might want to jot those down. You'll see those again on the concepts exam. One last thing before we do a little lab here. Pressure is the force that is acting on a surface due to the collision. So these guys here are all in motion, and as they move, they bash into the sides of the wall, and they push on it. and how much force you get divided by the area is equal to the pressure. So you can imagine as these molecules move faster and faster and faster, they exert more force on the wall and therefore more pressure. So what we're going to do is we're going to do a little lab. We're going to ask what happens in a container if the temperature goes up and if the temperature goes down. So what we got is this little gizmo, and in class we actually had this and we played with it. It's got a steel sphere down here that has molecules of gas in it. I think they're argon. And they're moving around, smacking into the sides, and this gauge measures that pressure. Okay? So the gauge measures the pressure, and what we're going to do is we're going to take it and first of all submerge it in boiling water. So here's a hot plate down here. This is water that is boiling, so those are bubbles on its surface. It's 100 degrees. You can see from the thermometer right here at 100 degrees. And the pressure is all the way up here. Here's 15, here's 16, here's 17, here's 18. So that's about 18.4 pounds per square inch. Okay? So when the water's hot, the molecules of air are moving very fast, and they bash into the side, and they make the pressure 18.4 pounds per square inch, or PSI. I then am going to take this thing, I'm going to submerge it in a bucket of ice water. So in ice water, the pressure drops, and we can see a close look at the gauge here. It doesn't drop to 0, it drops to about 13. Here's 14, here's 13, so that's about 13.8. So it dropped from 18.4 to 13.8 when we cooled it 100 degrees, from 100 down to 0. But clearly, it's not all the way to 0. So the question is, how much more would I have to cool it to get this gauge to go all the way to 0? The pressure will go all the way to 0 when the molecules stop moving and they're no longer colliding with the walls of the container. So in order to get the molecules to stop moving, the pressure would need to go to 0. And I want to know how cold do we have to get. So the directions are on canvas, and there's a page you need to print in order to make the graph. We're going to make a graph by hand. So you'll have to go to Canvas and read the directions. Here's kind of a summary of what you're going to do. You're going to make a scale where the temperature is on the x-axis and the pressure is on the y-axis. And you're going to take these 2 points we just found. So right here, the temperature is 100, the pressure is 18.4. Here the temperature of the water is 0 and the pressure is 13.8. So those 2 points, 100 and 18.4, and 0 and 13.8, you're going to plot on your graph. And it tells you on Canvas how to make the scale here. So you're going to plot these 2 points, and then you're going to draw a straight line through those 2 points, and you're going to extend that straight line to the left, we call this extrapolating it, until it crosses the x-axis. When it crosses the x-axis, that means the pressure is 0. So whatever temperature this is, that's the temperature we would have to cool the device to in order to get the molecules to stop moving. We call that absolute 0. All right? So you're going to take your graph paper that you're going to print from Canvas, make a scale on it. You're going to start at -500 and go all the way to 100. It tells you how much you're going to go up by 20s each time. You're going to make a Y scale. You're going to plot these 2 points, and then you're going to extend the line until it crosses. And you're going to try to estimate where it crosses the line here. That's absolute 0. Okay? So that's the little lab we did in class that you need to do. Once you do that, you can pick up tomorrow on what comes next.